Optimization. Optimization plays an important role in a wide range of disciplines, including engineering, physical sciences, econs, biology, data science, and so on. For example, scientists have studied how migrating birds choose an optimal velocity like v that maximizes the distance. So the distance as a function is maximized. They can travel without stopping, given the energy that can be stored as body fat. In linear regression, which is a hot topic for data science, we aim to find the best fitting line to set of data points. Mathematically, we want to find the parameters like slope and y-intercepts or the coefficients of the line that minimize the sum of squared differences between the observed values and the values predicted by the line. Here's how optimization comes to play. First, we come up with the objective function. The objective function we want to minimize, so this is our goal, is the sum of squared differences between the actual target values like y and the predicted values y hat by linear regression model. Mathematically speaking, it is expressed as the sum of y minus y hat to the second for all data points. One algorithm that you can use is gradient descent, which is commonly used in machine learning. It helps to minimize this objective function. In each iteration, gradient descent updates the parameters, slope, and y-intercept of the line by moving in the direction of steepest descent of the cost function. So basically, we come up with the mathematical model. We take the derivative, we set it equal to 0 to find the critical value or find the values that make the derivative doesn't exist. And then we continue the process. For example, a landowner has 2,400 feet of fencing and wants to enclose a rectangular area adjacent to a straight river for her chickens to roam freely. No fencing is needed along the riverbank. What are the dimensions of the field that maximize its area, providing ample space for the chickens? Well, here you have your rectangular land, and assuming that this part is adjacent to the river, and assuming that the chickens are not going to swim and run away, the area is x times y. X and y are the length of the sides. Please note that 2x plus y, so assuming that you have x and a y, 2x plus y, which is the sum of the lengths equals to the fencing, 2,400, you can isolate your y value. Your y becomes 2,400 minus 2x. Then you can substitute that into the area formula, which is ax. So wherever you see y, you're going to write 2,400 minus 2x. Now, you can basically simplify this by distributing x into parentheses, 2,400x minus 2x squared. Then take the derivative to find the critical value. The derivative of 2,400x is 2,400 minus the derivative of 2x squared, which is just 4x. Okay, let's just highlight this x here. Okay, now just set the derivative equal to 0 to find the critical value. So we set the derivative equal to 0 to find the critical value. X equal to 600 is the x coordinate of the critical value, and y is 2,400 minus 2 times 600, which gives us 1,200. So we found the dimensions of this rectangular, land that helps for the chicken to roam around a little bit, easy.